Hello everyone, Dr. Young here, and in this video I'm going to this is the first video of a whole bunch about stoichiometry. And so we're going to talk about what stoichiometry is, but most importantly, I want you to really focus not on that big funny word, but on this idea of mole ratios. You're just making up one new conversion factor, that's all we're doing, and then we can do a crazy amount of math. Most of the math that's done by people like me who are organic chemists. So to start off with, the word stoichiometry literally just means like element measuring. It's just a way to kind of measure and make relationships between elements. So let's talk about mole ratios and expand on this idea. First of all, just to make sure we're on the same page, you all have done ratios before. You know what a ratio is. It's just a useful way to describe the relationship between two things, right? And those things can be anything, right? There's ratios in recipes. There's ratios in determining how many representatives a state gets based on the population. There's ratios between all kinds of things. And you may have done problems like this in a math class before, but here's an example, right? If a factory has 5,528 wheels, how many tricycles can be made? And that's all the information you need because it's kind of implied that you already know what a tricycle is, right? A tricycle has 3 wheels, so you know that you need 3 wheels for every one of those bicycles. Now, what you're doing is you're making up a ratio, like we're going to make up more ratios here in a second, in your mind, and you're probably doing this problem already. I bet you could bust out a calculator and just do this, but I want to show you this real formally so that we can see the process and expand on it. When I look over here at this tricycle, right, here's my lovely little tricycle, I see that one tricycle has 3 wheels. Right, now we're back in grade school. One tricycle has 3 wheels. Check plus, smiley face. But another way to say this is that one tricycle has a relationship of, here, let's do this, not an equal sign, has 3 wheels. Right, for every one tricycle, there are 3 wheels. For every 3 wheels, there's 1 tricycle. And then we can kind of make this look even more like a conversion factor. I can say for every one tricycle, there are 3 wheels. And so I just took that observation, right, that when you have a tricycle, it has 3 wheels, and I turned it into a conversion factor, right? Here's my conversion factor. And that's going to allow me to solve this problem, right? Many of you are probably like, oh, you just divide by 3, easy breezy. But let's say you were not quite sure if you had to multiply or divide by 3. Let's figure out what that would look like. So you start with your known amount, right? Just like we do in all of our conversion factor problems. I've got 526 wheels. And then I need to put a conversion factor in here. Well, I just came up with one. One tricycle has 3 wheels. It looks like the way I wrote that happens to be the right setup where I need wheels on the bottom so that the units cancel out. So now my my wheels cancel out with wheels. I'm in units of tricycles now. And I just do that math, 5,526, yeah, times 1 technically, divided by 3, and that number comes out to be 1,842 tricycles. And so now I know how many tricycles could be made if I had 5,526 wheels. This process, which again is just the factor label method or dimensional analysis or unit conversions, whatever you want to call it, it's all the same thing, is super straightforward. The difference for us right now is that we need to come up with those ratios ourselves, right? This is what we're going to be doing for the rest of this video and for most of these other videos, is coming up with these conversion factors, these ratios. Only we're going to do it between the moles of things within a formula or between compounds in a equation. So let's look at this compound here, right? So here I have acetone, which is in most nail polish removers. So here's acetone. It's in nail polish remover. And I drew it out here. I don't care if you know what these lines and stuff mean at this point. What I do want you to see, though, is that this compound has 1, 2, 3 carbons, which is why I wrote C3 over here. And it also has 1, 2, 3, 4, 5, 6 hydrogens, so 6 hydrogens. And then lastly, 1 oxygen up here, so 1 oxygen up here, right? So this is the formula. This is the molecular formula. Of acetone. Now, I put that these are mole ratios within a compound. So what we're saying here is that this formula literally means, it can mean two things. This can mean, like I said in a previous video, right? This can mean for every 3 carbon atoms, there are 6 hydrogen atoms and 1 oxygen atom. And that is true, but that's just for like one molecule. And again, most people don't deal with one molecule ever because they're just so tiny. We deal with them in huge amounts, which is why we use moles. So another way we can describe this is that we can say for every 3 moles of carbon, right? For every 3 moles of carbon, there are 6 moles of hydrogen and 1 mole of oxygen. So what I can do is I can actually make a whole bunch of mole ratios, given that I know that that's the relationship between carbon, hydrogen, and oxygen for acetone specifically. So some mole ratios I can come up with here. I can compare any 2 things I want. So let's say I'm going to compare carbon and hydrogen. I can say that for every 3 moles of carbon, there are 6 moles of hydrogen, right? That would be a ratio I could come up with. And I don't have to include all of the elements in one ratio. Actually, you just pick any 2 things. You're just going to be comparing 2 things. I could also have said, okay, well, let's say I want to know the ratio between carbon and oxygen. Well, then I could say, well, for every 3 moles of carbon, there is 1 mole of oxygen, right? That's a mole ratio. It's a ratio comparing the moles within that compound. And I don't have to stop there, right? I could say, well, let's say we're going to compare how many moles of hydrogen are there relative to moles of oxygen. Well, I could say that there's 6 moles of hydrogen for every 1 mole of oxygen. And I wrote each of these one way, but there's no reason why I couldn't have flipped that. I could say for every 1 mole of oxygen, there's 6 moles of hydrogen. That's saying the same thing, right? These are supposed to be the same. Just like with other unit conversions, right? Just like saying that there's 6 inches in a foot is the same thing as saying that, 6 inches, 12 inches in a foot is the same thing as saying that 1 foot is 12 inches, right? It doesn't matter which one you say first. They're the same thing. So here I have written 3 different mole ratios for this compound. I have the green one, the purple one, and the red one. Are there any more that I can do for this? I've got carbon compared to hydrogen, carbon compared to oxygen, hydrogen compared to oxygen. Yep, I think those are just the 3. So if you're given a formula, you should be able to write these mole ratios. And again, what we're going to do in future videos, in future lectures here, is we're going to take these mole ratios so that I can say, well, oh, what if I have 147 grams of, or what if I have 147 moles of carbon? How many moles of hydrogen must there be then if we're talking about acetone? Or how many moles of oxygen must be in that if we're talking about acetone? So we're going to use this as a ratio, just like we did with the bike and the tricycle thing, the wheels and tricycles. We're going to use these ratios in conversion factors in future videos. So I can come up with more ratios within a compound, but I can also come up with more ratios between different compounds if I have an equation, right? If I have an equation. And on the put here, one thing that's really important is that you need to have a balanced equation, right? These mole ratios only work if you're talking about a relationship between things, and you don't have that relationship established if you have an unbalanced equation. So the first thing you need to do is make sure you have a balanced equation. Glancing at this one, I see already that it's not balanced, right? I have 4 carbons here and only 1 carbon on the right-hand side, so I know it's not balanced. Ditto, I have 10 hydrogens on the left and only 2 on the right, so I know it's not balanced. I'm going to go ahead and put these coefficients in here for us real quick. That would be a 4, that would be a 5, and we've got 13, 12, 6. So those should be the coefficients. And I can do the same thing, right? I mean, I could take something like this first compound, the C4H10O, and come up with a bunch of mole ratios within that one compound. But what I'm saying is I can look at this compound here, this guy, and then say, okay, well, what's the relationship? If I have one of those, how many oxygens do I need, right? So I can come up with a whole bunch more mole ratios and say, oh, well, apparently for every 1 mole of C4H10O, I need 6 moles of O2 because that's what the coefficients are telling us. Or I could say, oh, for however many of these C4H10Os I have, how many waters do I make? Maybe that's the question I'm after. I want to know how much water is produced from this reaction, depending on how many moles of C4H10. So I could say, well, for every 1 mole of C4H10O I have, apparently I need 5 moles of water, or I produce 5 moles of water. I produce 5 times as much water in terms of moles as I do of that butane. Or I shouldn't say butane, of that C4H10O thing. And I can compare any two things. It doesn't have to involve the first thing. It could be between, well, what's the relationship between carbon dioxide and water, right? I could have that one. I could say, well, for every 4 moles of carbon dioxide, if I make 4 moles of carbon dioxide, apparently I also make 4 moles of water from this reaction. Right? And again, you could go on and on. It can be any two things. I could say, well, if I produce so much carbon dioxide, how much oxygen is needed to do that? And I could do relationships between those. 4 moles of carbon dioxide for every 6 moles of O2, right? And so you just use those coefficients. And you can pick any two things you want. I'm going to stop here, but you can imagine I could keep on going. I could compare any two of these things. And again, I just want you to get the idea of that there are relationships between these two things. And we're going to use these in math questions later. That's what stoichiometry is all about, is the fact that we have to use a mole ratio at some point in the math problem. So I want you to take a minute and take a crack at these two questions. I have 2 equations here. I want to see at least 2 more relationships between within these compounds. So a bunch of stuff within this sodium sulfate and a bunch of stuff within this C7H6O thing, whatever it is. And then for the second one, write at least two more ratios between the compounds in the reaction below. And I already balanced it for you, so I kind of made that a little bit easier for you. But go ahead and pause and make sure you can draw some of these ratios, and I'll draw some of them in a sec. So hopefully you gave yourself a minute here to try to practice these, see if these make sense to you. I'm not going to draw all the possibilities for all these, but I'll draw a few of them. Hopefully you and I drew the same ones. And again, it doesn't matter if you drew yours upside down from mine. It's the same mole ratio. So if I wanted you to do this, I'd be looking for something like, oh, well, I know that for every 2 moles of sodium, there is 1 mole of sulfur. That would be 1 mole ratio. And if I wanted 2 mole ratios, that means I'd need to compare 2 other things. So maybe I'm going to compare the sulfur, 1 sulfur compared to those 4 oxygens, 4 moles of oxygens. And I should have mentioned this earlier, but notice that like all chemical equations, we're talking about moles here. We're not talking about grams of stuff. This is not like 1 gram of sulfur means that you have 4 grams of oxygen. These are counting things. We're saying for every 1 mole of sulfur atoms, you have 4 moles of oxygen atoms. They're not grams, they're not masses, these are counting things. We'll get into masses later, but these are not mass relationships, these are mole relationships. So here's 2 for the sodium sulfate. Again, if you'd flipped either of those upside down, that's fine. The other one you could have done is comparing sodium to oxygen would be the third one for this. And then same thing for the one on the right. Right, you could say for every 6 moles of hydrogen, for example, apparently there's 7 moles of carbon. Again, it doesn't matter if you draw one on top and one on the bottom, it's the same ratio. Or you could say for every 7 moles of carbon, there is 1 mole of oxygen. Those would be acceptable answers. Or you could have compared the hydrogen to the oxygen. That would have been fine too if you had that 6-to-1 ratio. Now for the last one, you can just pick like so many. I only asked for 2, so let's just pick the calcium to the calcium sulfate as 1. So I've got 3 moles of calcium. Apparently, I make 3 moles of calcium sulfate. Now you'll see in my videos and lectures and stuff, I go ahead and I keep the 3s there, Technically, a 3-to-3 ratio is a 1-to-1 ratio, but I like to keep it in there just to like doubly emphasize to myself that I'm following the equation. I'm following the coefficients in the equation. Mathematically, it's all going to equal out to 1 in the end anyways in this case, but I like to keep them in there. So I would like to see you put them in there also. Or I could have done 1 mole of, let's say, the aluminum sulfate. It will give me 2 moles of straight up aluminum. All right, so I picked those two. You maybe could have picked comparing calcium to aluminum, or maybe you picked aluminum sulfate to calcium sulfate, or any other combination therein. So if I was asking you these questions, these would be great answers for these questions. So make sure that these make sense to you, practice, study, and then start watching the next video where we're actually going to do math using these mole ratios. Good luck.